Well, I would like to start by just telling that when Sam asked me to do this talk, I said, well, Sam, I'm really not working on Mars. I'm really not doing any of this. He says, no, that's all right. Just show them how you build and integrate a payload and fly it on station as a development test and go through your experiences. So, in a sense, I feel like a fish out of water, or maybe a Martian off the planet of Mars, whatever. But so let's just talk a little bit about in-orbit servicing, where we've been, where we're going, and why. And I can't forget to mention that we are on station on this experiment that's launching on the 28th of June, we hope, Shuttle 135, and that we have the Canadians are here, and they're one of our associate partners on this experiment. And I want to make sure that I don't forget to mention them, or I will pay the price. Okay, so where have we been? Well, we've been involved in satellite servicing since 1976. In fact, we're just tonight having our 30th anniversary in satellite servicing. So it's kind of ironic that we should have this presentation. But we started off with manned space flight servicing. And guess what? We're still doing and interested and concerned and focused on the ability of humans to do manned space servicing, but this time it's at remote orbits. This time it's L1, L2, Mars, GEO, and so on. And of course you have these practical limitations in the near-term time frame. The near-term time frame in the next 5 to 10 years in terms of radiation, transportation capabilities to go to L2 and L1 and so on. So that doesn't stop us from the overall goal of being able to commit ourselves to the economic benefits, and I want to underscore the word economic benefits of being able to repair and maintain satellites anywhere, anytime. And so our objective right now in the next 5 years is to do it robotically. So robots is what we're in the interim all about. But eventually, we realize that it's going to take some of these sophisticated repair activities on Mars and an L1 and L2 are going to take neurosurgeons in orbit like we did on the last servicing mission of Hubble. And John will be able to speak to that, but it's truly, in fact, neurosurgery. So what you want to do with robots is to have them in front and will take the humans along with them, but keep them protected in a safe environment in the interim. So, in a sense, we're really still about manned space, repair, and maintenance. But the future is now, is what I tell my folks. And at my age, you can understand why I would say that. so let's take a look quickly. There is a little bit of spin-off here that I would say in this effort, near next 5-year effort to develop the maturity necessary. And that spin-off has to do with fuel depots and in-orbit repair and maintenance, being able to rendezvous with these vehicles, being able to do the pose estimation, being able to do all of this activity robotically and, yes, autonomously. Because our target systems are the challenges of yesterday. Our target systems are the spacecrafts that were designed not for in-orbit repair and maintenance, but only for ground assembly and test and fueling. So in effect, our targets are latency. Our targets are all those systems that are in the $500 million to $2 or $3 billion price range, wherever they are, to be able to go up there, repair them, refuel them, service them, sometimes super sync them, and take care of those benefits. Now, with that level of maturity, you can see how this can spin off to operations on or near the surface of Mars. And I just heard this morning's presentations, and that sunk right in. So we've been conducting robotically a series of studies over the last 18 months. Involved the entire aerospace community, invited them in, have had several workshops, all focusing on what are the needs of the customer, and then what are the technologies today to be able to go take care of those needs. the most principal and significant aspect of all of this is the nearby customers, the nearby clients, I could use that word, or spacecrafts that need fuel or repair, are in orbits like geo orbits, like 98.5 degrees sun sink, like L1 and L2. Those spacecrafts are all designed prior to even a thought about satellite servicing. No grapple fixtures, no corner cubes for autonomous approach and repair, all of those kinds of things missing. So we have to deal, and our objectives in life is to go deal with latency systems with that kind of capability. And that puts a great, great drive on what you do with your repair system. What you do with your spacecraft is going to be your tow truck in orbit, because that's really what it drives. So the customers told us two things today are preventing them most significantly about even considering repair and maintenance. One of them is the ability to in-flight refuel when their systems have never been designed for automated approach, repair, and refueling, especially the refueling part where everything is safety wired down, everything is covered with MLI, and so on. So that's one of the major targets. And the second is the ability to approach and rendezvous and make sure you're going after the right spacecraft. And if that spacecraft happens to be tumbling, understand that it's tumbling, understand that it's spinning, and put yourself at the same rate. That is, put this tow truck at the same rate and the same spin as the spacecraft you're about to capture, and then go forward and capture it. So those two things are what we're focusing on with station experiments. And as I say, the first one, dealing with in-flight refueling, is been delivered to the Cape, and we're ready to launch in June of this year. So let's take a look at it. It sits on the outside of station, and it sits on a platform in that great big box with a robot that's looking over it, being the Dexter robot, built by the Canadians. And the blue device being a set of special purpose tools that go after the specifics of latency refueling systems that were last seen by technicians on the ground when they put the safety wire on and wrapped them up with MLI. So these are the special tools, and I guess I would say the precision of the system and the dexterity of the system rests with these semi-autonomous tools that have two TV cameras. You can see the cameras in the center. Let's see if I can. The camera here and a camera here, and then an artificial lighting system here, and then the tools right down the middle. Electronics package buried in the center of this, and you'll see a film on that. Here's a technician holding one of the tools. This happens to be our in-flight refueling tool, and it's got a quick disconnect that is assembled on this latency spacecraft after the safety wires are cut and removed. Now, we have a quick film, and I'm going to quickly run through the film. But up on the left-hand corner is a picture of the 600-pound module that's been delivered to the Cape. Down below is the robot going through the activities of pulling out a tool and then coming forward, again, semi-autonomously, understanding what it's looking at, comparing it against an image that it has buried inside of its computer, and going after and cutting the safety wires. In this case, it's a series of cryogenic valves for a cryogenic exchange system. And you can see the wire cutter going forward, spotting the wire, cutting the wire, and then he'll change. The robot will come forward, put that tool away, grab another tool, and a special purpose end effector. Now keep in mind, this is done semi-autonomously, so we can stop it, but it's already programmed where it's going to go next. We can stop and change the program, but generally speaking, it works on its own. And in this case, it's getting a special tool to go after these T-valves and disassemble the T-valve, which has already had its wire cut. But you can sort of get now the idea of what you're going to see in orbit on an average of 3 days every month for a period of about 2 years, doing these specific tasks, including a refueling task in which we put a referee fluid into that module and into a receiver tank that acts very much like a spacecraft, and disassemble a ground-based refueling connector. So I'm going to, what you're seeing there is a series of steps in which the tools are locked into place and then unlocked so that we don't have any tool flying around the station. And it's going now after a cryogenic in-flight refueling cap, and then it'll go after a plug. I'm going to try to drop this and go to the next view graph because of the time limitation. Okay, so that's the first experiment. The second one we want to do approximately a year and a half later, and it's the approach and rendezvous and docking of a spacecraft never been designed to be captured, doesn't have any capture fixtures, any grapple fixtures, any retroreflectors, any fiducial marks or anything. What we do have, though, on the ground is a picture of what that back end of that spacecraft or side of that spacecraft looked like before we lifted off. And that's a key facet because the computational system we have on board, the Chase vehicle, has the capability of doing instant recognition of an image that's embedded in its computer against what it's seeing on this target vehicle, and then turning around and computing the differences until it gets the two images to merge, to look like one. And at that point in time, we're about 1 meter away from the spacecraft we're about to capture. And that includes tumbling. So what we have to do that is we're using the 55-foot ISS RMS, and we're using, again, Dexter. And on the end of Dexter, we have this package made up of sensors: flash LiDAR, TRIDAR, optical sensor, IR sensors. And that combination feeds its signal into a special processor, an FPGA computer, which we call the Cube. And that does the processing and commands both the vehicle and the arms in position to do the capturing. Now, our ultimate goal is to basically build such a system and fly it and go after some of these very expensive assets, either in low Earth orbit or in GEO. Our first customer right now appears to be NOAA with GOES 12, which is running out of fuel, and which has a very important assignment to do weather assessments in around the South American region. And that's just one. Now, I realize there's several different companies doing this, and I think that's just terrific. And that we're another is just wonderful, because where would Ford be today without a GM? Or without a Toyota, or without a Honda, right? And then those of you that say, well, you know, this is really passé, this business may not ever materialize. And there's a company called Austin Wells. Has anybody ever heard of them? In 1890, they were one of the premier builders of horse-drawn wagons in the United States. Right? By 1910, they were out of business. So I'm saying to you as a community, the future is now. We got to look forward, not backwards. And if we buy an automobile and expect to drive that car till it breaks and then turn it in and buy another one, I don't think we'd stay alive. I think we'd go bankrupt. Correct? Do we buy an automobile so that, in fact, when we drive it out of that factory or out of that showroom, we can never come back? We have to go buy another one? No, we wouldn't do that. Why do we do it with spacecrafts? Why do we allow ourselves the economic inflexibility of not being able to repair and continue the operation of those systems? A good example of that, a perfect example of that is Hubble. Designed for 10 years, gone to 21, 22, 23 years now, and still producing breakthrough science. Will probably operate for 25 or 30 years. Where's the return on investment on that? Probably pretty significant, right, John? You tell them at dinner, would you? Okay. All right. So now I'm trying to wrap this up, but I think if I could say anything about, how am I doing on time? I'm over. All right, okay. So all I can say is it's been a very interesting experience working with Station. It's been a learning experience. But we've been working with Shuttle for some 30 years. And I would say it's just another step along the way. And it's something we have to collectively, the Shuttle program, the Station program, and us, we have to keep driving this system. And if we don't do it often enough, we'll never drive it to where it's streamlined and cost-effective for people to process on board. So thank you very much, Sam.